Now we're going to talk about two different counting principles. The first one is the addition principle. So it says if one event can occur in ways and a second event with no common outcomes can occur in different ways, then the first or the second event can occur in m plus n ways. And the key word for these is usually total. So or and total are two different ways to signal an addition principle rule. And when you read these, you're going to think, I've known this forever. So it says, if you have 6 pairs of wool socks and you have 8 pairs of cotton socks, how many total socks do you own? This is technically an addition principle rule. We want to know the total. There are two different types of socks, right? They have no common outcomes. It's either a wool sock or a cotton sock. There's no way for those to overlap each other. We're assuming in this case there's no wool cotton blend sock. So you simply add these together is what it's saying. 6 ways plus 8 ways equals 14 total socks. So don't overthink those. The multiplication principle is slightly more difficult, right? So we're not going to keep it so easy. The multiplication principle says, suppose that there are k operations to be performed in a sequence. So that's kind of what changes these, like there's a sequence to it. The first operation can occur in 1 ways, and for each of these, the second operation can occur in 2 ways, and the third operation can occur in 3 ways, and so on and so forth. Then what it says is that there are in 1 times in 2 times in 3 times all the way up to however many you have in k times to perform all of these operations in a sequence. And we have what we call a tree diagram, which is a pictorial device that helps us to keep track of all the different ways in which a sequence of choices can be made. So notice, sequence of choices is what differs here. Okay? So let's do an example to see how these work. This says, a die is a cube with faces numbered 1 through 6. So I think we all know what a die is. Construct a tree diagram showing the possible results for when a single die is rolled and then a single coin is flipped. So notice there is a sequence of events happening here. First, we're going to roll the die, then we're going to flip the coin. So let's draw out what this would look like. So a tree diagram starts at the left and it goes out to the right and it has branches. So the first level is going to end up having 6 branches to it, because when you roll a die, what you could roll is you could roll a 1, 2, 3, 4, 5, or 6. So all those numbers go on my first level branches. So notice my N1 basically is 6. There are 6 different ways, 6 different outcomes that I could get when I roll this die. Now as a tree branches, so do our tree diagrams. So for the second level, we're going to flip a coin. When you flip a coin, you either get a heads or a tails. So off of each one of these, so off of the 1, I branch off twice and I label them H and T for heads and tails. And I do the same thing off of the 2 and the 3 and the 4 and the 5 and the 6. So it starts to get a little crowded sometimes. My N2 is a 2 because at each level or at each branch here, I had 2 choices, 2 ways when you flip a coin, 2 things could happen, heads or tails. So if I want to look at all the different things that could happen, I basically follow my branches out. So I follow this first branch out and it goes 1 and then H. So the set 1H is the first outcome, the first set that I can get when I do these 2 things in a sequence. And then the next one would be follow the branch to the 1, but take the T branch after that. So 1T would be the next outcome. And I could continue in this manner. I could get a 2 and an H or a 2 and a T. And I'm not going to write them all out, but I could write them all out if I wanted to see them all. But what we really want to know is just how many. We just want to know how many are there. So what this says is this is a multiplication rule. I'm going to take 6 times 2 and get 12. There are 12 total outcomes here, and we could continue to write them all out. So that's how a multiplication rule works. Let's do one more with our tree diagram. So this says to construct a tree diagram showing the possible results when a coin is flipped 3 times in succession. Okay, so for my first level, we're going to flip a coin. So there are 2 options there, which is heads or tails. And then for our second level, we're flipping the coin again. So we branch off twice again from each one of those and label again heads or tails on each one of those branches. And then our third branch is actually just another repeat of the same thing. So off of each one of our endings so far, we do another 2 branches, labeling them all H or T, H or T, H or T, H or T. So now if I wanted to look at the possible results, my top branch would be heads, 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 H, 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 that's set. And then my next branch would be H, H, but take the T branch, so H, H, T. And then I could get an H, T, H. And an H, T, T. And again, I could write all of these out. I could continue on in this fashion. But what we really want to know right now, and there's sometimes when we want to know what all of those are, so you could continue and get all of them if you need to write that out. But what we're really concerned about right now is how many are there. So notice at every level there are 2 outcomes. So I have a 2 times another 2 times another 2, which gives us 8 total outcomes. So although these may seem fairly easy right now, they will get more difficult, and they're also building blocks to other more difficult problem types later in more advanced content. So this is how I suggest doing them now so that you build good habits for later. So you don't always have to draw the tree diagrams. Some will suggest that you do or tell you to do it, some won't. So if you're not drawing a tree diagram, this is how you should do it. You should draw the amount of blanks that you need, the number of operations that have to be performed, fill each blank with the amount of ways that each operation can occur, and then do your multiplication. Okay, so let's try these next 2 without any diagrams. So this just says a woman has 6 different pairs of pants, 8 different blouses, 5 different pairs of shoes, and 3 different purses. How many outfits consisting of 1 pair of pants, 1 blouse, 1 pair of shoes, and 1 purse can she create? So she's going to go through this sequence of choosing. I'm going to choose a pair of pants, I'm going to choose a shirt, I'm going to choose my shoes, and then my purse. Okay, so it looks like there are 4 blanks we need to write because there are 4 different choices that have to be made. And I put the little multiplication symbol in between all of them because this is a multiplication rule. So whatever they get filled in with, we're going to multiply them together. Okay, so the first one is going to be pants. I'm going to write PA below that for pants. All right, she's got 6 different choices for pants, so that blank gets filled in with a 6. And for her blouses, she has 8 choices. And for her shoes, she has 5. And for her purses, PU, she has 3 choices. So if we multiply that all together, what's 6 times, I did it out of order, 5 times, that's okay, 8 times 3. She could make 720 different outfits by combining those items. So these do get really big, really fast, the answers do. Okay, what about a license plate that is going to consist of 3 letters A through Z, followed by 3 digits 0 through 9? How many different license plate combos are possible? Okay, so there are going to be 3 letters, so I need blank times blank times blank for that, and then 3 digits, so 3 more blanks, times blank times blank times blank. So 6 total blanks here. Now, for the letters, A through Z. So how many choices are that? You need to know how many letters are in the alphabet. There are 26 letters in the alphabet. So for each one of these, there are 26 different choices. Notice they didn't say anything like without repeats. So I could make these all AAA if I wanted to, or ZZZ, or I could do ABA. Every combination of all of those will work. So there's 26 times 26 times 26 ways to pick your letters. And then your digits, the digits 0 through 9, that's 10 different digits there if you count them. So these next three would be 10 times 10 times 10. So we're going to do 26 times 26 times 26 times 10 times 10 times 10. And that gives us, okay, let's see. I always write it down and then I go back and put my parentheses in, or my commas in so that I can really read that off. So it looks like 17,576,000 ways to make these license plates. So you can see why picking a license plate that has already been used before should be a fairly rare thing to have happen to you. Oops.